Hello students, welcome to ALPHORES e-learning channel. This is K. Nageshwar Rao, your physics faculty. Today we are about to deal with session number 47. In this session, we will discuss about riverboat model. In the previous session, we have discussed about rain umbrella model, and in this session, we will discuss about riverboat model. Riverboat model or river swimmer model, both are similar. In place of boat, we can imagine swimmer, and whatever theory we will be developing, that theory can be applied for river swimmer model as well. Okay, so let us see what this riverboat model is. So riverboat model. Before we go into the theory, we go deep into the theory. Let us define few terms here. I'm going to define few terms. V subscript r. This is velocity of river flow. Velocity with which the river is flowing. This is with respect to ground. Okay. So the other one is velocity of boat with respect to river. VBR. Velocity of boat with respect to river. River in the sense here, especially in this case, when the river is not flowing, when it is in still condition, when it is not flowing, when it is a still condition, whatever velocity the boat can maintain in the river, that is VBR. Whatever this VBR is there, that is the velocity of the boat in a river which is not flowing, Okay. If the river is flowing, what happens? The resultant velocity of the boat will be different. We all know that if a boat is driven along the direction of river flow, what happens? We see boat moving with more velocity, because to its velocity, river velocity gets added. If at all, if a boat is supposed to move against the river flow, what happens? It moves very slowly. When compared to the previous case, it moves slowly because it is moving against the river flow. Okay, so whatever velocity it has got, that will be suppressed with the velocity of river flow, with the what a river opposes the motion of the boat. So because of that, what happens to the resultant velocity of the boat? It gets suppressed, it decreases. This is our usual experience. We all know that. And if at all, if river is moving at some angle with the river flow, depending upon at what angle it is moving, different kinds of scenarios will arise. So in this session, we will be exploring all these details. So all that we should know is, depending upon angle between these two physical quantities, we will see different possible cases in this situation. If VR, river flow direction, and VBR, velocity of boat with respect to river, both are along the same direction, the boat moves very fast. If velocity of river and velocity of boat with respect to river, if they are opposite to each other, boat moves very slowly because boat is being opposed by the river flow. River flow, what it does, it pushes the boat in the backward direction. If at all, boat's velocity is less than river flow, and if a boat is trying to move against the river flow, what happens? It cannot move. It will be drifted along the river flow, isn't it? So depending upon angle between these two physical quantities, here we can make an analysis of possible situations, possible cases in case of riverboat model. Okay, so I hope all of you have got an idea what we are about to deal with. So let us go ahead. I am going to define one more physical quantity. It's a VBG, velocity of boat with respect to ground. Velocity of boat with respect to ground. If someone is observing from the ground, okay, the direction along which the boat moves, along that direction what lies? Velocity of boat with respect to ground lies. Maybe if I am driving the boat, okay, if river is flowing along this direction, let us say I am driving the boat along this direction. So as long as I am driving, I will be thinking that my boat is going along this direction. But if somebody is observing from the ground, he will observe the direction of boat in some other direction, because the river flow is pushing the boat. So the resultant path will be different. I don't, maybe being a driver of that boat, maybe I see always boat oriented along this direction. But if somebody is observing the boat from the ground, they will see the boat moving in some other direction, not along the direction, in which the boat is driven. Okay, so let us try to understand these details very much. Depending upon angle between these two, let us talk about a few details. Let theta is equal to 0 between VR and VBR. Okay, So what is the angle between VR and VBR? It's 0 degree. It means VR and VBR both are along the same direction. It means if water is flowing along this direction, okay, river water is flowing along this direction with a velocity VR. Along the same direction, boat is also moving. Velocity of boat with respect to river. So both are along the same direction. Okay. So in this situation, what happens? What will be the resultant velocity? Velocity of boat with respect to ground. Let us try to understand that. Here, resultant velocity of boat, which is velocity of boat with respect to ground, is equal to velocity of boat with respect to river plus velocity of river. That's how you can talk about magnitude of resultant velocity. In vector form also you will get like a VBG bar is equal to VBR bar plus VR bar. Okay. So let us take it as equation number 1. Okay. What if theta is equal to, let us say, 180 degree? If theta is equal to 180 degree, that is the boat is moving upstream. In the previous case, the boat is moving along the stream, along the downstream, or here what? Downstream. Okay. So in this case, if theta is 180 degree, this angle is between what? Between VR and VBR. If theta is 180 degree, what does it mean? The boat is moving upstream against the river flow. In this situation, the resultant velocity of the boat with respect to ground can be written as VBR minus VR. Let us take it as equation number 2. Let us take it as equation number 2. Both are opposite in direction. Both are opposite in direction. Okay. Now, I will imagine a situation here. Let us say the boat is somewhere here and it has traveled down the stream up to here. Okay, up to here it has traveled. Let velocity of river is VR. From here to here, let us say the distance of separation is d. Distance of separation is d. So I'll assume that it has traveled downstream once and it turned back and it has come back to its initial position. It has traveled back a distance equal to again d. So it has traveled downstream through a distance equal to d, and again it has turned back and it traveled upstream a distance equal to d. So let us try to find out how much time it takes. In the when it is traveling downstream, I'll assume that the time taken is t1. How much is the distance traveled by the boat downstream? D. With what velocity it has traveled? It has traveled with a velocity equal to VBR plus VR. So let us take it as equation number 3. When it is traveling in the upstream, again the same distance d. How much time it will take? Let us assume that as t2. So let us say t2 is equal to d by what is the velocity when it is traveling upstream? VBR minus VR. VBR minus VR. Okay. Now if you observe these two equations, here the denominator value, numerators are anyways the same. Here denominator is more in the first case when compared to the second case. If denominator is more, this t1 value will be less, isn't it? If this value is more, t1 will be less. It means when the boat is traveling downstream, very quickly it was able to cover distance equal to d. But whereas when it is traveling up the stream, this is the resultant velocity and this value is less when compared to this one. If this is less, this t2 value will be more when compared to t1. It means when it is traveling upstream, it takes more time to cover the same distance because it has to overcome the resistance offered by the river flow, isn't it? So it's a common experience, all of we know that, but mathematically, this is how we can put all these details in the form of equations like this. Okay, so the total time taken for this journey, therefore, total time taken is t is equal to t1 plus t2. What is t1? It's d by VBR plus VR plus d by time taken for the upstream journey VBR minus VR. So that's how you can talk about total time taken. Okay. So this is one possible case. What? When theta equal to 0 degree, when theta equal to 180 degree. Theta equal to 0 in the sense both VR and VBR are along the same direction. It means the boat is traveling along the downstream. Okay. And when theta is 180 degree, it means VR and VBR both are opposite in direction. It means boat is traveling up the stream. Okay. So this is how the details can be handled. So now, apart from traveling downstream and upstream, if boat travels at some angle with the river flow other than 0 and 180 degree, so what is going to happen? Okay, let us see that. So let us say the boat is traveling at some angle with the river flow. I will consider that situation. Okay, it's a general case. General case. Whatever details we have dealt with earlier, all those details can be obtained from these conclusions. Whatever equations I will be, concluding here, from those equations or previous equations can be can be obtained. Okay, so this is a general case. I'll consider a river of width equal to d. So what is the width of the river? D, and this width is uniform width. Of course, practically that's something that is not possible, but we'll assume that whatever river flow we were considering here, okay, so that is of uniform width. Okay, so this is one river bank, this is the other river bank. So the separation between these two river banks is constant along the flow of boat or along the flow of river, and that distance of separation d, or that is called as river width, where d is what? Let d is equal to river width. Okay. Now, somewhere here, let us say the boat has started and it was driven along this direction. So the boat is driven along this direction. So this is what? Velocity of a boat with respect to river. Velocity of boat with respect to river. Let us say the river flow is along this direction. So this is what? River flow direction. River is flowing from left to right, in this direction it is flowing. Okay. So definitely, the boat, the resultant path of the boat won't be along this direction. It will be something else. It will be something else. We don't know. It all depends on how much velocity the boat has got with respect to river. That is going to decide in which direction eventually the boat will be traveling with respect to ground. If I am observing from the ground, definitely I will not be seeing this boat traveling along this direction. Its path will be something else. But as long as the driver of the boat is driving, always he maintains the direction of velocity of the boat along this direction only. But if I am observing from the ground, I don't see this boat moving along this direction. Let us take it as AC. So I don't see this boat moving along this direction. I'll be seeing along some other direction. In what direction it moves? It will be decided by the magnitude of velocity of boat with respect to river. At what speed the boat is driven, that is going to decide eventually what path the boat will be taking. Okay. So I'll consider a few more things here. Let us say the angle made by velocity of boat with respect to river with this line is theta. Okay. It means in this case, angle made by velocity of boat with river flow is how much? 90 plus theta. So the angle between river flow and velocity of boat is how much? 90 plus theta. So here, angle between VBR and VR is 90 plus theta. This is the angle. Okay. Now, I will resolve this VBR into two components. Since it is making an angle theta with this line, along this line, what component I can have? I can have VBR cos theta, and in this direction I can have cos sine component, right? VBR sine theta. So from our vectors conceptual knowledge, we know how to resolve a given vector. So this is how this VBR can be resolved into two components. Okay. So this is what? VBR cos theta, this is VBR sine theta. Now look at this one. Whatever VBR is there, it has been resolved into two components, and those two components were doing two jobs. One component VBR sine theta, its job is it has to overcome VR because both are opposite in direction, right? So when the boat is traveling along this direction, a part of its velocity is engaged completely in overcoming VR. And the other part is engaged in taking the boat to the other bank, Okay, so this VBR cos theta will take the boat, to the other bank across the river, and this VBR sin theta, it is completely engaged with VR. it is supposed to oppose the river flow. It is supposed to face the river flow. If at all, if VBR sin theta and VR both are equal in magnitude, VBR sin theta and VR both are equal in magnitude, you know what happens? The the effect of these two things becomes 0, isn't it? Because both are equal in magnitude but opposite in direction. So the resultant value will be 0. In that case, the boat travels along this direction. The resultant path of the boat will be along this direction. What if VBR sin theta cannot overcome VR? Let us say VR is greater than VBR sin theta. It means river flow is dominating. You know what happens in that case? The boat will cross the river, but it will end up somewhere here. Because VR is more when compared to VBR sin theta. Since VR is dominating, the boat will be pushed more and more towards what? Right side, and somewhere here it may end up, somewhere here it may reach the other bank. If at all, if VBR sin theta is greater than VR, it means VBR sin theta component is dominating now. So the boat will reach the other bank somewhere here, to the left of this point. Let me take this point as B. Let me repeat this again. If VBR sin theta, VR both are equal in magnitude, the resultant value will be 0 because both are opposite in direction. No? So the resultant velocity will be 0. So in that case, the boat will reach exactly this point B. Exactly this point B. Normally on the other bank, whatever point is there, it meets there. Okay. If VBR sin theta is greater than VR, it means river flow is not sufficient to overcome this component. So since this component is dominating, the boat will end up somewhere here to the left of point B. Whether it will reach this point or this point or this point, it all depends on what? Magnitude of VBR. Magnitude of VBR. More the velocity of a boat with respect to river, it will end up somewhere here. If it is slightly less, maybe somewhere here it may end up. If it is exactly equal to VR, it will reach this point B. If it is less than VR, it means river flow will dominate now. So it will reach somewhere here, isn't it? So the value of this VBR sin theta is going to play a crucial role in deciding where the boat will meet the other bank. Okay, so let us try to understand few other details connected with this picture. Okay, so here what component of velocity of the boat is playing a vital role in taking the boat across the river. So this VBR cos theta is taking the boat across the river. But at what point it will meet, whether towards left of B or towards right of B, where it will meet, that is going to be decided by VBR sin theta. And who is taking it across the river? VBR cos theta. So that's how the two components of VBR are engaged in two different tasks. So let me find out a time in which it crosses the river. Time taken by the boat to cross the river. I will take it as t. Time taken is equal to distance by velocity, right? So how much distance it has to cover normally? D distance. And what is the component of velocity which is taking the boat along this normal direction? VBR cos theta. So this is how time taken by the boat to cross the river can be expressed. Okay. Let us talk about one more point. For example, the VBR sin theta value is less than VR. Then what happens? The boat will end up somewhere here. Somewhere here it will end up, isn't it? And in how much, when it is when it is reaching this point, what is happening here? In fact, the boat's velocity is maintained along this direction, but because of river, the boat gets drifted, towards right of point B. Towards right of point B. Let the boat got drifted by a distance equal to x. So how much is the drift in the boat along the river flow? X. That x can be calculated. Distance is equal to what? Velocity into time, or speed into time. Here, what is the speed with which it gets drifted? It undergoes drift if VR is greater than VBR sin theta. So with what velocity it undergoes drift? With a resultant velocity it undergoes drift. What is the resultant velocity? VR minus VBR sin theta, isn't it? So here the resultant velocity with which it undergoes drift is VR minus VBR sine theta. And in how much time it undergoes drift, for how long it undergoes drift, equal to time taken by the boat to cross the river, this t. So finally this equation becomes VR minus VBR sine theta into, what is t here? D by VBR cos theta. So this is how the drift and time taken by the boat to cross the river can be obtained. Now see, when the boat is trying to cross the river, it may, out of our discussion, you can easily understand that it can cross along the shortest path. See, this is what the shortest path is, right? Any other paths are not shortest paths. And also it can cross the river in shortest time. Shortest path is this one. Don't think that since the path is short, time taken by the boat is also, to travel along that path, it will be what? It will be small. No, it's not like that. See, when the boat is traveling along this direction, okay, if VBR sin theta, VR both are equal, then what happens? The boat travels along this path AB and it reaches exactly the opposite point. And that's what shortest path is. And here what is happening? The boat is engaged in overcoming the river flow. Some resistance is offered by the river flow, and continuously the boat is engaged in overcome that resistance. What happens if you drive the boat initially along this direction itself, instead of driving the boat along this direction? If you drive along this direction, now resistance offered by the river flow will be less, isn't it? When it is traveling, the water is pushing the boat. When the boat is traveling along this direction, what happens? The resistance, comparatively, resistance offered by the river flow to the boat is less. So in that case, you can consider this situation as river flow is favoring the boat. Here, when the boat is driven along this direction, river flow is opposing the boat's motion. So when it is traveling along this direction, initially, if the boat is driven along this direction, you can assume it as the river flow is favoring the boat's motion. So if that is the situation, there is a chance for crossing the river very quickly. Like in the case of downstream, river flow and boat's velocity gets added, and at a very high speed boat travels down the stream, isn't it? So to cross the river, let us say, if the boat is driven along this direction, maybe very quickly it can reach. I'll tell you about that. If it is driven along this direction, in this case also, if the initially velocity of the boat is along this direction, then also what happens? Of course, river flow favors the boat's motion, but we don't know where it will meet the bank, here or here or here, or it continuously moves along the direction of river flow, and it may meet with the other bank after traveling a drift equal to 1 kilometer or 2 kilometers. We don't know that, and for that time may take more, isn't it? So to deal with shortest time taken by the boat to cross the river and shortest distance along which the boat can travel, we need to have another approach. Okay, I'll discuss those two things as two special cases. And in this case, if you wanted to write a velocity of boat with respect to ground, that can be written, but we don't know in which direction it is going. Whether it is going along AB or along this direction, we don't know. Okay, but in the rest of the cases, we can write a velocity of the boat with respect to ground also. Okay, let us see those cases. So now let us discuss about these two possible cases. One is crossing the river in shortest time. The other one is crossing the river in shortest path. So in the previous discussion, we came to know that yes, boat can be driven along shortest path, and boat can also be driven in shortest time across the river. But it all depends on in which direction you are maintaining velocity of boat with respect to river. Right. If it comes to the case of crossing the river in shortest time, I already told you, if the boat is driven along this direction, normal to the river flow, then what happens? The river flow will push the boat along this direction, and the resultant path of the boat will be along this direction, and somewhere here it will meet with the other bank. Okay. If at all, if the boat initially, if it is driven along this direction or along this direction, what happens? The river flow gets added to the boat's velocity, and the boat may meet the other bank somewhere here or somewhere there. It gets drifted along the river for a long distance, isn't it? If that is the case, it may take more time to cross the river, isn't it? If at all, if we take the boat along this direction, the resultant path of the boat is along this direction. To make sure that resultant path of the boat is along this direction, what you have to do? You have to drive the boat along this direction initially, so that what happens? The river flow pushes the boat, and finally the boat takes this path. If somebody is observing from the ground, they will see the boat moving along this direction. Okay, whether it moves along this direction or it goes along this direction or it goes along this direction, it all depends on VBR magnitude. Okay, we will assume that VBR value is such that the resultant path of the boat is along this direction, and this direction is what? It is having shortest path, isn't it? If the boat is starting from this point A and if it is meeting at point B, okay, so this AB is the possible shortest path. If at all, if boat meets somewhere here, that is not the shortest path taken by the boat. If boat meets somewhere here, that is not the shortest path taken by the boat. This is the only path. Normal distance of separation between the two banks is the shortest path. Okay, so let us discuss these two things. So we came to know that if the boat is supposed to cross the river in shortest time, the boat should be driven along the normal between the two banks of the river, so along this direction. So this is what velocity of boat with respect to river is maintained along this direction. So because of river flow, eventually the boat has taken this path. The boat has taken this path. If someone is observing from the ground, this person will be seeing boat traveling along this line AC, traveling along this line AC. So let us try to find out a few physical quantities, few parameters associated with this case. What is our first primary interest? We wanted to find out shortest time of journey. So I have already assumed that since it is it is traveling along this path, resultant path is this one, so it is taking shortest time. That's what our conclusion was. So if that is the case, the time taken to cross the river, it can be written as how much is the distance traveled? D distance, equal to width of the river. With what velocity it is traveling along this direction, whatever velocity is there, you can take that velocity. So VBR. Okay, or else what you can do is you can take this path AC, we don't know AC length, and divide that with VBG. Then also you will get shortest time taken. Or you can take width of the river D, and along this width of the river, what is the velocity existing here? VBR is the velocity along the width of the river. So D by VBR is also what? Shortest time taken by the boat to cross the river. And the second one that we can talk about is magnitude of this VBG. This VBG magnitude, this is a right angle triangle, isn't it? So VBG can be written as under root VBR square plus VR square. Okay, and the next one is the angle made by the resultant path of the boat with the normal of the river. Okay, river flow. With this normal, how much angle it is making? Theta angle. So let us try to find out that angle. Tan theta. What is tan theta from the figure? This is the opposite side, VR. Adjacent side is VBR. So tan theta is equal to VR by VBR. That implies theta is equal to tan inverse of VR by VBR. So that's how you can find out the angle made by the resultant path of the boat with the normal drawn between the banks of the river. Okay, and the next one is you can also talk about drift. Here along the river flow, the boat velocity is maintained along this direction only, but finally it has met with the other bank at point C. So along the river flow, how much is the drift? How much is the distance traveled along the river flow? BC. So let us try to find out that BC. Drift along the river flow. Along the river flow. How much is that? BC. That distance can be, how it can be calculated? Distance is equal to speed into time. With what speed it got drifted? With a speed equal to VR. And in how much time it has undergone that drift? Equal to this time taken by the boat to cross the river. During that time, the drift is going on. Okay, so here this T is what? D by VBR. So VR into D by VBR. So that's how few parameters associated with crossing the river in shortest time can be concluded. Let us get back to this one. Crossing the river in shortest path. So if you are supposed to cross the river in shortest path, what is that shortest path? This is the shortest path. So if you wanted to have your boat traveling along this path, you are not supposed to drive the boat along this path. If you drive the boat along that path, what happens? If boat is driven here along this path, finally it is meeting somewhere here. Is this the shortest path? No, it's not shortest path. So if you want your boat finally taking this path, you have to drive the boat along this direction, making some angle theta with the normal between the river banks. So in this case, let us try to find out the time taken, or let us start with the angle. At what angle the angle between the normal to the flow of river and VBR. Okay, how much is that? From this triangle, right angle triangle, let us consider sine theta. I have taken sine theta because usually we will be given with these two details, velocity of boat with respect to river and velocity of the river. Whenever any question is there, very often what are the details given? Velocity of the river and velocity of the boat with respect to river. If at all, if VBG is known to us, we can take tan theta also. Okay, since these are the two details I am starting with in this discussion. Okay, these are like known parameters. In terms of these known parameters, what I can write? I can write expression for sine theta, isn't it? So sine theta is equal to opposite side VR by VBR. That implies theta is equal to sine inverse of VR by VBR. So this is the angle made by velocity of boat with the normal between the banks of the river. The second one that we can talk about is magnitude of this VBG. VBG magnitude, this is a right angle triangle, right? So this is adjacent side, this is opposite side, this is hypotenuse. So VBG can be written as under root hypotenuse square minus opposite side square. That's how VBG can be written, isn't it? And the third one that we can talk about is what is the angle made by velocity of boat with the river flow. How much is that angle? Angle between VBR and VR, that is equal to how much? This is 90 degree. So 90 plus theta is the angle between river flow. So this is the direction along which the river is flowing, isn't it? So what is the angle between river flow and velocity of the boat? 90 plus theta. And the other parameter that we can talk about here is the time taken by the boat to cross the river. How much is that? Time taken is equal to distance it has traveled along this path, isn't it, finally? So D, width of the river. Width of the river is how much? D divided by what is this VBG? Velocity of boat with respect to round, and that VBG can be replaced with this one, under root VBR square minus VR square. Okay, so that's how the river boat model can be handled. So these are the possible situations with river boat model. Now let us try to solve two problems based on this river boat model. Now let us solve these two problems. The first one is a boat takes 2 hours to travel 8 kilometers and back in still water lake. So the water is not moving in the lake, it's a still water lake. So the boat has taken a time equal to 2 hours to travel 8 kilometers and back. It means it has traveled 8 kilometers and it has come back again by traveling a distance equal to 8 kilometers. For that, for this entire journey, 8 kilometers plus 8 kilometers, how much time was taken? 2 hours of time is taken. Okay. With water velocity of 4 km per hour, the time taken for going upstream of 8 kilometers and coming back is. Now in the second case, what he was saying that the river flow is there and the river flow is maintaining a velocity equal to 4 km per hour. So the water in the river, in the lake, it's flowing with a velocity equal to 4 km per hour. Now in that lake, upstream, the boat has traveled upstream a distance equal to 8 kilometers and again it has traveled downstream a distance equal to 8 kilometers. So we have to find out the total time taken. Okay, so we can handle this one. This kind of model related theory we have already discussed. So let us try to find the answer. So here velocity of the river, how much is that? 4 km per hour. Velocity of the river is 4 km per hour. Okay. What about velocity of a boat with respect to river? This is not given directly, but whatever data he has given, from that data we have to find out. What is this velocity of boat with respect to river? In the sense, when the river is not flowing, at that time, whatever velocity the boat has, that is velocity of boat with respect to river. Of course, right now we are dealing with a lake. Let us say in the lake, the boat has traveled a distance equal to 8 kilometers in one direction. In the opposite direction, it has traveled again 8 kilometers. The river is not flowing in this case. The boat takes 2 hours to travel 8 kilometers and back in still water lake. So what is the total distance traveled here? Total distance traveled is 8 plus 8 is 16 kilometers. And in how much time it has covered this 16 kilometers of distance? 2 hours. Therefore, velocity of boat with respect to river is equal to 16 by 2, 8 kilometer per hour. Okay. So now we have obtained VBR. How much is VBR? VBR is equal to 8 kilometer per hour. Okay. So now the river is flowing. River is flowing. Okay. So the boat has started from this point. Let us say the river is flowing along this direction. With what velocity it is flowing? It is flowing with a velocity equal to 4 kilometer per hour. So the boat initially it has traveled upstream up to, let us say, a distance equal to how much it is given? The time taken for going upstream of 8 kilometers and coming back. So it has traveled a distance equal to 8 kilometers upstream and it has come back again. Along the downstream it has come back. So the total time taken, how it can be written? Time taken is equal to, in case of upstream, how much, whatever distance it has covered, I'll take that distance as d, divided by with what velocity it covers that distance when it is traveling upstream. Velocity of a boat with respect to river minus velocity of the river. Regarding this we have already discussed. Plus, during downstream, velocity of boat with respect to river plus velocity of the river, both gets added, isn't it? So again, how much a distance it has covered? It has covered a distance equal to d divided by VBR plus VR. So this time is related to downstream journey. This time is related to upstream journey. Okay. So now let us replace these values. What is the d given? 8 kilometers. So 8 by VBR is how much? 8 minus VR is how much? 4 plus 8 by 8 plus 4. So what you will have? 8 by 4 plus 8 by 12. So here 2 here. So 2 plus 2 by 3, which is equal to 8 by 3 hours. 8 by 3 hours. So in terms of minutes, 8 by 3 into 60, 20. So what you will have? 160 minutes. So how much is the time taken by the boat to complete this entire journey? 8 kilometers upstream and 8 kilometers downstream. How much time it has taken? 160 minutes. So this is how it can be solved. Now let us look at this problem. What is this? The velocity of water in a river is 2 kilometer per hour. So velocity of the river is given, while width is 400 meters or 0.4 kilometers. A boat is rowed from a point, rowing always aiming opposite point at 8 kilometer per hour of still water velocity. Still water velocity in the sense when the river is not flowing, at that time whatever velocity the boat is having, that velocity is 8 kilometer per hour. So this is nothing but velocity of boat with respect to river. So here velocity of boat with respect to river is given. How much is that? 8 kilometer per hour. Velocity of the river is also given. How much is that? 2 kilometer per hour. Width of the river is also given. How much is the width of the river? 400 meters. Or this can be written in terms of kilometers as 0.4 kilometers. So these are the details given. So what you have to find out? On reaching the opposite bank, the drift obtained is. It was mentioned very clearly, the boat is rowed from a point, rowing always aiming opposite point. So if this is the river, let us say somewhere here the boat started its journey. So it is rowed always aiming the opposite point. So along this direction, okay, velocity of boat with respect to river is maintained. We have already seen this case. If this is the situation, in shortest time boat will cross the river, along this path, isn't it? And if you take this as A, let us say this is B, this is C, and this BC is what? Drift along the river flow, and that's what he is asking us to find out. On reaching the opposite bank, the drift obtained is, and this BC can be calculated like this. We have already seen the theory. BC is equal to, along this direction, what velocity exists? Velocity of the river. Distance is equal to speed into time. In how much time it crosses the river? It crosses in a time equal to d by VBR. Isn't it? So what is VR? VR is given as 2 kilometer per hour, d is 0.4 kilometer, and VBR is 8 kilometers. So what you will have, 1 by 10 kilometers, 1 by 10 kilometers, or in terms of meters, how it can be written, 100 meters. 1/10 of a kilometer is equal to 100 meters. So along the river flow, to what extent it undergoes drift? It undergoes a drift equal to 100 meters. So this is how river boat model problems can be handled. If it is river swimmer model, just imagine in place of boat, imagine swimmer and try to solve the problems in a similar manner. Okay. So thank you, students. With this I will close the session. Okay. Thank you.